Hi, everybody. Now that we've talked about the range and the kernel of a linear transformation, and of course the rank and nullity that goes with it, and we have the rank nullity theorem out of the way, I'd like to go and talk about a related topic called when a function is one-to-one and onto, in the case of linear transformations. Now, the reason we do this is because back in college algebra, if you remember, we did it quickly. In order to show that a function has an inverse, you want to show it's one-to-one. For linear transformations, we also need onto-ness because we want to make sure that the inverse mapping can be applied to the entire codomain. So we need onto-ness to guarantee that we can do that. So first, what do we mean? We will say that a linear transformation from V to W is one-to-one if and only if that if you ever have two vectors in V, so their images T of U and T and V are the same, then the vectors U and V are the same. We will say that the linear transformation is onto if and only if for every single vector W in the vector space W, there is some vector V in V so that T of V is W. In other words, every single vector in W has a pre-image, or every single vector in W is the image of something in V. Now there's something else here that's nice, that the one-to-oneness, the way it's defined, it's done that way because it's easy to prove things if we express things in terms of equality. But it's a lot easier though to understand and what it really means if you look at its contrapositive. So the contrapositive of the exact same statement is that if U and V are vectors in V and U is not equal to V, then we have that T of U is not equal to T of V. One-to-oneness means that if the inputs are different, the outputs are different. In terms of graphs, and what you learned a long time ago in college algebra, that means a function passes the vertical line test. It's just, this is the algebraic way to describe such a thing. Okay, you just need pictures to understand what these things mean. So generically now, I'm not writing down all the vectors. I'm only drawing a couple in every vector space. So the picture on the left describes for you a transformation between two vector spaces V and W. In this case, that transformation is definitely one-to-one because the image of everything between any two different inputs in V gives you different things in W, but it's not onto because one of the vectors has no image, is not an image of some vector in V. In case in point, it's actually this guy right here. It's not the image of anything. The second picture I gave you is an example of a transformation that is not one-to-one, but it is onto, because every vector in W is the image of something from V. But it's not one-to-one because there are two different vectors in V, but they get mapped to the same thing. You can't have that. Different vectors have to get mapped to different things if it's one-to-one. Doing it again. Again, on the left, this is a transformation that is one-to-one and onto. The one on the right is a transformation that's not one-to-one and not onto. These four different pictures are here to show you that one-to-oneness and onto-ness do not need to be the same thing at all. They do not need to imply each other. They do actually, if we have one more condition. That's what I'm aiming for the rest of this video. All right, so what you need to be able to do is if I give you a transformation, you can convince me that it's not one-to-one by counterexample, or convince me it's not onto by counterexample. Counterexample means give me some vectors that violate the property. For example, for this first transformation D, it's the derivative operator, going from the set of polynomials of degree 2 or less to the set of polynomials of degree 1 or less, just by doing the derivative. I want to know that is that one-to-one or not. So a good way to do this is you're looking for some kind of collapsing where two vectors get sent to the same thing. Well, a good way to do that is probably if there's collapsing, it comes about because of the kernel collapsing to one vector. So let's just see, is there two vectors that get sent to zero? Are there two or at least two vectors in the kernel, something other than the zero vector? And yeah, actually, if you take the derivative operator to the function 1, you take the derivative operator to the function 2, you get the zero vector, the zero function. So D is not 1-to-1. Easy. The second one, I need to know, is this thing 1-to-1? Well, to do that, I'm going to use the fact that I remember the kernel because we computed it. The kernel of T happened to be the span of the vector 1 minus 2x. So if I take T of 1 minus 2x, it will be the same as T of any multiple of it, 2 minus 4x, because the kernel is a subspace, so multiples of it are back in that space. This will then be the 0, which in this case is 0, the real number 0. So T is not 1-to-1. Easy, right? Now you may want to know, why would a function not be onto? You need to know what the range looks like then in general. So I actually gave you the range for this one. The range of this transformation was equal to the span of, it was 0, 1, -1, 0. So all I need is just some matrix that's not in that span. So there is not a matrix A in M22. So S of that A would then be 1, 0, 0, 0, because this vector is not in the span. That's not in the span of the matrix I gave you. Therefore, hence, S is not onto. Not onto. Great, easy. It's easy. In order to find out when a function is 1-to-1 or onto, you're actually just considering the kernel and the range and interpreting it in some way. Let's try one more time. This time I did not give you this before. Can I think of a vector that is in the codomain, but is not a possible output? Well, I need to know the output set. Well, so then this transformation, which I'll just call T, say R, don't know why I called it R, T. This transformation T is applied to a polynomial of degree 1 or less, that's this guy. But the result is then x times that. So that'd be a times x plus bx squared. So is there something that's not here in the range? Well, yeah, constants, right? There's no way to get a constant out of that. The result can't be constant because it's always x times the thing. So there is no vector. So T of that equals 1, for example, can't be done. Hence, T is not onto, because there's something that's not in the range. Cool. So then what you need then is a way to kind of take the results you just saw and collapse them down into a nicer statement. Well, to do that, notice that the kernel, if the kernel was not just a 0 vector, that instantly implied that it was not 1-to-1. The reverse is actually also true. So as long as you have a transformation between two vector spaces, the following three things are equivalent to each other. The kernel of T is the 0 vector. T is 1-to-1, and the nullity of T is 0. Now, two of these is obviously automatically equivalent. The kernel of T being the 0 vector and the nullity of T being 0. It literally, they mean each other. It's just definitions then. The other one is a little more interesting. It's actually this implication here that you might feel a little leery about. Proving it's incredibly easy. I'm just not interested in doing it all. So I'll only prove one of the directions. So let's go and assume that T, that the kernel of T is just the 0 vector. Let two vectors u and v be in V, so T of u equals T of v. I'm going to show you that u and v are the same. Then, if that's true, then T of u minus v would be then T of u minus T of v, but since they're equal, that subtraction is a 0 vector. consequently, we have that U minus V is in the kernel. Hence, U minus V has got to be the zero vector because there is only one vector in the kernel. So that subtraction being in the kernel has got to be it. And so U minus U is equal to V. And that's why I had to show. So then it's definitely one-to-one. So if the kernel is the zero vector, then the transformation is automatically one-to-one. And the vice versa is also true. All you have to do is just literally reverse this argument pretty much in order to show you that the kernel here is just a zero vector. We also have a, that's a typo right there. This should then be not about the kernel and one-to-oneness. This is about the range and onto-ness. If you have a linear transformation between two vector spaces and W is finite dimensional, it's a little additional thing, and W is finite dimensional, then the following things are equivalent. The range of T is W. That can only happen if T is onto. That can only happen if the rank of T is the dimension of W. Now, some of these are just literally the definition. The range of T is W and T is onto, they literally mean the same thing. They are literally the same statement when you write it down in terms of symbols. That the range of T is equal to W and the rank of T is equal to the dimension of W. Again, that's something we already know. The only one that we don't have, the reason we have to insist that W is finite dimensional is the reverse part right here. If the rank of T is the dimension of W, this implies that the range of T is equal to W if and only if, where we don't, well, not if and only, but we're guaranteed it's true if W is finite dimensional. It's weird, but it is possible that the rank of T and the dimension of T, the dimension of W are infinite. And yet the corresponding spaces are not equal to each other. An example of that would be like the vector space of polynomials inside the vector space of continuous functions. Their dimensions are equal, they're both infinite, but they're certainly not equal to each other. There are functions that are continuous that are not polynomials. So we need that the codomain is finite dimensional to guarantee that all three of these are equivalent. Okay, again, I'm not interested in really proving this, but I am interested in using it at least a couple times because there's a cool trick at the end that we get at for free. So I'm going to show you what the nullity of this particular transformation is. And I called it R all over again. Since I call it R multiple times, now let's call it R just once. So, I'm going to show you that what the nullity is. Once we know the nullity, we can then find out that R is one-to-one, but it's not onto. Why? Because we know that the kernel of this R is just a zero vector. The reason is that if this is going to equal zero, the only way that's possible is that this is zero. So then the only way that can be zero always is that it has to be the zero vector itself. So the kernel of this thing is zero. So the nullity of this transformation is also zero. But that means then that the rank of this transformation, that's the dimension of P2 minus the nullity of the transformation. And that's 2 minus 0, that is 2. So that means then, hence, that R is 1-to-1 as the nullity is of R is 0. But R is not onto as the dimension of the target space P3, and that dimension's 4, does not equal the rank of R, which is, oh wait, the dimension of P2, that's 3. Oops, 3, and that's 3. There we go, fix it. And that's 3. So this side's 4, this side's 3. They're not equal to each other. So then R can't be onto. So it's not onto. So we know it's 1-to-1, we know it's not onto. Do it again. I want to show that this particular transformation is not one-to-one, but it is onto. So the argument's exactly the same. I'm just going to look at the nullity, and we know the kernel for this guy. We've computed it before. So the kernel of T was just the span of the vector 1 minus 2x. So the nullity of T was 1. It requires only one vector in its basis. But then, therefore, the rank of T is equal to the dimension of P1 minus the nullity of T, and that's 2 minus 1, that's 1. So T is onto. And that's because the rank of T being 1 is equal to the dimension of the set of real numbers, which is 1, because they're both equal to 1. But T is not 1-to-1, and that's as the nullity of T is not 0. That's it. That's that one. Really easy. One more time, but this time an extra little layer here that's kind of fun. I'm going to show you they're both onto and 1-to-1. The only difference I have between this example and the ones that came before is that the dimensions of the codomain and the domain are the same. So let's see what happens. So I want to know what the kernel is. If I know the kernel, I can go and find out what the nullity is. I need the kernel of this thing. Well, the kernel would be the set of all vectors, set of all polynomials. So it gets mapped to the 0 vector. In this case, the 0 vector would be the vector of all zeros. That would then mean that A plus B would have to be 0, and A plus 2B would equal 0. But that means A equals B equals 0. So the only polynomial of degree 1 or less that gets mapped to the 0 vector in R2 is actually the 0 polynomial. So that will be only the 0 vector. So I now know the nullity. So the nullity of T is 0. It's instantly now 1-to-1. But by the rank theorem, notice that the rank nullity theorem, the rank of T is equal to the dimension of P1 minus the nullity of R2. And notice that this is the same as the dimension. This is actually also the same as the dimension of R2. So this would then be 2 minus 0, which is 2. So T is 1-to-1 as the nullity of T is 0. And T is onto because the dimension of the target space is equal to the dimension of P1, but that's equal to the rank of T plus the nullity of R2, but that is the rank of T because this guy is 0. Notice I never actually needed to compute this, did I? I never needed to know that the rank of T was 2. Because the minute the dimensions are the same rank, once the dimensions of the two spaces of V and W, of the domain and the codomain, since they're the same dimension and the nullity is 0, instantly the thing had to be onto. That is a very neat little argument, which is really useful. So we're going to write it down. So summarizing that very last result, if you have two vector spaces that are both finite dimensional, and you have a linear transformation going between them, if their dimensions are the same and the transformation is 1-to-1, you instantly get it's onto. You don't need to prove it. If their dimensions are the same and T is onto, you can actually reverse my argument and show that it's 1-to-1. So that's really nice. You never actually have to show both that it's 1-to-1 and onto. The minute you show one, you automatically get the other, provided the spaces are both finite dimensional and equal in dimension. If they're finite dimensional, but not equal in dimension, this may not be true. This won't be true. Actually, probably very likely won't be true at all. Okay, cool. So then you have that. And I believe that's enough for that video.